Hello everyone. Today we will discuss how to prove outer measure of an interval is its length. So the proof is going like we are having three cases. In the first case we are taking I equal to closed interval AB. In the second case we are taking I to be bounded. In the third case we are taking I to be unbounded. That is, we are taking that interval to be unbounded. So we can start with I equal to closed interval AB. So we are taking I equal to closed interval AB. Now let epsilon greater than 0. Let epsilon greater than 0. We know that this closed interval AB is a subset of open intervals A minus epsilon, B plus epsilon. This is true because when we take a real line, I am having my A here. This is the real line, and here I am taking B. Then obviously for any epsilon greater than 0, A minus epsilon will be in the left of A, and B plus epsilon will be in the right of B. So we can write like closed interval AB is a subset of A minus epsilon, B plus epsilon. Then we can write we have the monotonicity property of outer measure, which says that if A is a subset of B, then it implies that M star of A, that is outer measure of A, will be less than or equal to outer measure of B. This we know. So using this we are applying this here. So what we can write, M star of closed interval AB is less than or equal to length of A minus epsilon, B plus epsilon. We are taking this M star of A minus epsilon, B plus epsilon, because what is outer measure? It is infimum of all this length. So we know that. So I am taking not I am taking that infimum. I am taking that length. So what is this length? This length is equal to B minus A plus 2 epsilon. So we got that M star of closed interval AB is less than or equal to B minus A plus 2 epsilon. It holds for any epsilon greater than 0. If we take any epsilon, this will hold, which implies that M star of closed interval AB is less than or equal to B minus A, because it holds for any epsilon greater than 0. So call it equation number 1. What we need to show that M star of closed interval AB is equal to B minus A. Now we have proved an inequality, that is M star of closed interval AB is less than or equal to B minus A. What we need to show now, next we need to show that M star of closed interval AB is greater than or equal to B minus A. So to prove this, we are taking, let collection IK from K equal to 1 to infinity be a countable collection of open bounded intervals covering closed interval AB. So that we can write closed interval AB is a subset of union K equal to 1 to infinity IK. We can write like this. Then outer measure of closed interval AB will be equal to infimum of length of IK. This we know. So if I am taking like this, we need to show that M star of closed interval AB is greater than or equal to, closed interval AB is greater than or equal to B minus A. And we know that M star of closed interval AB is this infimum of summation K equal to 1 to infinity length of IK. So it is enough to show that summation K equal to 1 to infinity length of IK is greater than or equal to B minus A. Call it equation number 2. We are just used this. We have to prove this, and we know that M star of closed interval AB is infimum of summation K equal to 1 to infinity length of IK. So instead of infimum I can take like this. I don't want that infimum. Then also I will get the inequality like this. So it is enough to show that this inequality holds. So But by Hein-Borel theorem, we have any collection of open intervals that covers closed interval AB has a finite subcollection that will always cover closed interval AB. So we have taken this collection covers closed interval AB. So by Hein-Borel theorem, it has a finite subcollection which covers closed interval AB. So what we are going to do is choose a natural number n for which this collection ik from k equal to 1 to n covers closed interval AB. Okay. Now we will show that summation k equal to 1 to n length of ik is greater than or equal to b minus a. Instead of showing for k equal to 1 to infinity, now it is enough to show that for k equal to 1 to n length of ik is greater than or equal to b minus a using Hein-Borel theorem. So this is equation number 3. So now only we need to show this equality, this inequality. If this inequality holds, then equation 2, this inequality will hold, then which will imply m star of closed interval AB is greater than or equal to b minus a. So for that, what we are taking, we will show that this happens. So we have closed interval AB is a subset of union k equal to 1 to n length of ik. This we have. So which implies that closed interval AB is contained in this union. So which implies that A is an element of union k equal to 1 to n ik. So which implies that A is an element of some ik for some k. Is an element of ik for some k where k is from 1 to n. So we call that ik as open interval A1B1. That is, A is an element of open interval A1B1, and this open interval A1B1 is in this collection ik. Collection ik, k is from 1 to n. This open interval A1B1 is from that. So A is an element of open interval A1B1. Now we can discuss like this. So this is the real line. So this is my A1, and this is my A, and this is my B1. So my B can come here or here. If my B1 is greater than or equal to B, that is B is somewhere here, my B1, so I am taking my B1 is greater than or equal to B, then I can write summation k equal to 1 to n length of ik is greater than or equal to B1 minus A1. How it comes? Because this A1, B1 is one of these intervals in this collection, and we have taken the sum of all the intervals in this collection, and it will be obviously greater than the length of one interval in that collection, that we know. And look here, B1 minus A1, it will be always greater than B minus A. So this is clear from this figure. So I can write it is greater than B minus A. Now, if B1 is greater than or equal to B, we have taken like this. Otherwise, what will happen? B1 will be somewhere in closed interval A open. So here it will change to this. B will not be here. That is what we are going to say. B is somewhere here. B is somewhere here. So we will say that if B1 is greater than or equal to B, this happens. Otherwise, B1 will be an element of closed interval A open B. So we can say that B1 will be an element of closed interval A open B. So, but B1 is not an element of open interval A1 B1. This we know. Okay, but so B1 is an element of closed interval AB. So there must be an interval in this collection which contains B1. Call it as open interval A to B2. Call it as open interval A to B2. That is, B1 is an element of open interval A to B2. So Now we have A2 is less than B1 less than B2. Now again consider a figure like this. That is, we are considering like this. We had A1 here, and then we had B1 here, and we had a here, and we have taken that A2 and B2, A2 and B2 somewhere. We are not bothered about A now. We have taken some A2 here, and we have some B2 here, and we have taken that this B is somewhere here. B is somewhere here, or it can be here. If we are taking that, if B is somewhere here, I am taking like this. Okay, I'm taking like this. If B is somewhere here, that is B2 is greater than or equal to B. So if if B2 is greater than or equal to B, then what will happen? Summation k equal to 1 to n length of ik will be greater than or equal to B2 minus A2 plus B1 minus A1. How this happens? Because we have taken only the sum of two intervals in this collection ik from k equal to 1 to n. It will be always less than or equal to the sum of the whole interval in that collection. So I can write this B2. I am giving some rearrangement here. So B2 minus A2 plus B1 minus A1. I can write like B2 minus A2 minus B1 minus A1. There is nothing wrong here. So I can write like this. Then when we check here, what is A2 minus, here we have an A2 minus B1, isn't it? When we check here, what will be A2 minus B1? A2 minus B1. So we are subtracting a term which is greater than A2 from A2. B1 is greater than A2, and we are subtracting that B1 from A2. So it will be a negative number. So this A2 minus B1 is a negative number. Here we have a minus. So it is a positive number. Here we have a positive number. So it will be always greater than B2 minus A1. We can write like this. B2 minus A1. So what is B2 minus A1? B2 minus A1. When we look at this, A is somewhere here or here or here, somewhere here is A. Our A is. So B2 minus A1 will be greater than, I can write B2 minus that A1 is greater than B minus A. So what we got? Summation k equal to 1 to n length of ik is greater than B minus A. So we are continuing in this way. This process, this selection process will terminate because we have taken this collection ik from k equal to 1 to n. So there are only n intervals. So it will terminate at some stage. So we obtain a subcollection, collection AKBK from k equal to 1 to capital N. I am taking that terminating step as N, capital N, which is a subcollection of collection ik from k equal to 1 to n. So what are the peculiarities of this collection AKBK from k equal to 1 to n? We have A1 is less than A, and AK plus 1 will be less than BK for 1 less than or equal to k less than or equal to n minus 1, and Bn will be greater than B. It will be clear from the figures. When we consider this figure, all these are saying. We are generalizing this through this. Okay. Then, so we can get summation k equal to 1 to n length of ik will be greater than or equal to summation k equal to 1 to capital N length of AKBK, because this AKBK, collection of AKBK is a subcollection of this IKs. So we can write like this by monotonicity. So length of AKBK. So what is length of AKBK from k equal to 1 to n? That is Bn minus An plus Bn minus 1 minus An minus 1 plus etc. plus B1 minus A1. this is what our length of AKBK summation this. So I am going to rewrite this. Some rearrangements are given. That is, I am taking like, I am writing it as Bn minus An minus Bn minus 1 minus etc. minus A2 minus B1 minus A1. I can write like this. As we have done earlier, we got a negative number, isn't it? We got a negative number here. Like this, I am going to write these terms like this. So these all terms becomes positive, a big positive. Here we have minus. These are negative, but due to this minus, so it is going to be positive number. So it will be greater than Bn minus A1. Then again, this Bn minus A1 will be, which will be greater than B minus A. So what we got summation k equal to 1 to n length of ik is greater than or equal to B minus A, which was our third equation to be solved. So equation 3 solved implies m star of closed interval AB is greater than or equal to B minus A. Equation 4. Equation 1 we had m star of closed interval AB is less than or equal to B minus A. So these 1 and 4 implies that m star of closed interval AB is equal to B minus A. That is, for closed interval we have shown that outer measure is its length. Now we will move to the next case. Case 2. Case 2, what it says, we are taking I is a bounded interval. I is a bounded interval. So if I is any bounded interval, given any epsilon greater than 0, there are two closed bounded intervals. Closed bounded intervals J1 and J2 such that J1 is a subset of I, subset of J2, while length of I minus epsilon is less than length of J1 and length of J2 is less than length of I plus epsilon. We can write like this because we have taken I is a bounded interval. So I is a bounded interval. For any epsilon greater than 0, we can find two closed bounded intervals J1 and J2 such that this will happen. Like this interval we can find, and length of I minus epsilon will be less than length of J1 and length of J2 will be less than length of I plus epsilon. So first we are taking this inequality, that is length of I minus epsilon is less than length of J1. So we have taken J1 as a closed bounded interval. For a closed interval we have shown that outer measure is its length. So we can write like m star of J1. It is equal to m star of J1. And we have this J1 is a subset of I. So J1 is a subset of I. What does that imply? M star of J1 is less than or equal to m star of I by monotonicity of outer measure. So we can write, I can write m star of I. Now again using this, m star of I will be less than or equal to m star of J2. I am writing in the next page. It is less than or equal to m star of J2. Well, J2 is a closed interval, so it will be equal to length of J2. And length of J2 we have, length of J2 is less than length of I plus epsilon. So we can write it is less than length of I plus epsilon. So we reach the inequality like length of, so I am taking a different color, length of I minus epsilon is less than or equal to m star of I, which is less than or equal to length of I plus epsilon. That is, we have reached an inequality like m star of I, that is, we have reached the inequality like length of I minus epsilon is less than m star less than or equal to m star of I less than or equal to length of I plus epsilon. So it holds for any epsilon greater than 0, implying that length of I is equal to m star of I. Thus we have proven for bounded interval. Now we are taking for unbounded interval. So we are taking in the case 3, we are taking I to be an unbounded interval. For an unbounded interval, if I is an unbounded interval, then given any natural number n, we can find an interval j, which is a subset of I, such that length of j is equal to n. We can find any interval of length n, I being unbounded, we can take like j is a subset of I. So, m star of I, by monotonicity, m star of I will be greater than or equal to m star of j. And j is an interval, so we have its length. We can find an bounded interval or like that. So, we can say that it will be equal to length of j, that is equal to n. That is m star of I is, m star of I is greater than or equal to n. It holds for any natural number m, which implies that m star of I must be equal to infinity. Thus the proof. Thank you all.